Hello everyone. Discuss contest 6. Contest 6 was surprisingly hard, especially last few problems. So I didn't expect it again to be that hard. So people, problem is a lot of people ask me to make contests harder because they are too easy and they do not learn anything new. Sometimes I try to include some harder problems like this H, for example. It's not super hard. So I will explain you the whole solution. It's actually pretty simple if you know what you're doing. Okay, surprisingly, nobody solved it, even in upsolving. Maybe that's because it's not something that people know how to do nowadays. So last problem is about backtracking. So you need to carefully implement some backtracking algorithm. That's something that was popular some time ago, but not now. So now students don't know how to implement backtracking models. In old days, everybody know how to implement simple recursive backtracking, but now it's forgotten knowledge. Okay, so we'll go for problems one by one, talk about them like we normally do before. Problem A. Now, problem A is pretty simple. So you have some students. For each of them, you know how many times they already participated, and they know they can participate at most 5 times. So you need to pick ones who can participate at least k more times. Yeah. So if they need to participate k more times, then currently they participate less than 5 minus k times. So you pick all these students and form teams of 3. So number of teams you can form is just number of students divided by 3. Nothing really to talk about any problem. So let's see the solution. So that's the whole solution. So we read input, count number of elements less or equal 5 minus k. So if it's less or equal minus k, then we can increase it by k. So we want to participate k times, and we can participate at most 5 times. Yeah. So if your current number is x, you increase it by k, you have x plus k. It should be less or equal than 5. You can rewrite it like this. Yeah. It will be the same thing. Yeah. So you can count number of good elements divided by 3, get number of teams you can get. That's it. Pretty straightforward. No surprises actually here. Let me check if someone managed to fail it. No. Okay, I didn't solve it from second try. Okay, so someone solved it from the second try. Okay. First problem is boring. Let's go to the second problem. Probably it will be a little bit more interesting. Second problem, a little bit more interesting, but still pretty straightforward. So we have some picture basically of characters. So each character represents some color, and this picture, colors form some rectangles. So it's guaranteed that each color represents some rectangle, and we need to count how many rectangles have common border with the given rectangle. So we have one rectangle with this color R. Yeah. Here it is. And we need to find all the rectangles which have the common border with this one rectangle. That's it. So let's just do it. So what I will do? I will many ways to do it. So I believe a lot of possible implementations of this idea, but what I'm doing, I will just look at all neighboring cells. So I will look at all pairs of neighboring cells. So if one of the cell is my target color, then I will mark this cell as one of the neighboring. So I will just count all different colors which have neighboring cells with the cell of the target color. Yeah. That's it. And I will put just all of them into the set. So I'll do it like this. Yeah. So here, so these two loops, they look at all neighboring cells in horizontal. So horizontal neighboring cells. So I have cell AJ and cell IJ and cell IJ plus 1. Yeah. So I take these two cells and look at their colors. Here I copy pasted the code 4 times, to here and to here also. Not the best code style, but again, for easy problems it should work. So if X is a target color and Y is not target color, I put Y into the set. Yeah, and vice versa. If Y is good color and X is not, I put X in the set. So now now this set contains all characters which have common border with the target characters. Yeah. And then I do the same for vertically neighboring cells. Yeah. Just copy paste this code again. Change this I to n minus 1, m minus 1 to m, and here I change ij plus 1 to I plus 1j. Yeah. Everything else is the same. That's it. That's it. So I check all neighboring pairs here, all neighboring pairs here. Now I check all possible pairs of neighboring cells. In the end, I erase dot from this. I figured out that I forgot that I also have these dots. Dots just empty cell. I don't need to count it, so I just erase it in the end. I can also modify these ifs so I don't consider empty cells, but I thought it would be easier just remove it in the end. Okay, again, it's not the clearest possible code, so probably if problem is a little bit more harder, I would think about simplifying this code, because for hard problem you have much more code and it is much more intense, so you kind of want to make it short so you have less number of mistakes. Yeah. But for easy problems like this, it's okay. So even if you copy paste code 5 times, yeah, if it's simple code, you can probably find the mistake easily, even if it's copied 5 times. So not a big problem. That's it. So that's problem B. Let's look at your submissions again. Let's check. Okay, let's pick one. Okay, let's look at you. I just hope to find code which is more clear than mine. Oh, that's actually nice. Yeah, that's basically the same, but a little bit shorter, you see? So you check over all pairs, not to n minus 1, n minus 1, but just to nm. Yeah. And here check. So if you find the cell of the target color, so this is the color I'm looking for. I look at 4 neighbors of this cell, just like this. Yeah. And I check if this neighbor exists, then I add this neighbor to the cell. And in the end, I just erase this target color because it's not neighbor of itself, and remove empty cell. Okay, this code is actually easier than mine. Yes, I agree, but not that much. Okay. Okay, let's go next. Oh, C is interesting mathematical problem actually. So here finally you need to think. We have some numbers and we want to make them equal. Yeah. So we want to make them equal by multiplying them by 2 and 3. So we can double the number or we can triple the number. And we want to make all the numbers equal by applying these operations. How we do it? That's basically. So imagine you have two numbers. Imagine you have two numbers like x and y. Yeah. What's happening? I multiply them by 2 a couple of times. So x multiplied by 2 number of a, 3 on b, equals to y multiplied by 2 power c and by b power d. Yeah. Now, since this, now, how do you think? Okay, since this problem is about powers of 2 and 3, so it should be something about prime numbers. Yes, so we multiply only by prime numbers 2 and 3. So let's look at these numbers x and y. They also contain some prime divisors 2 and 3 inside of them. Yeah, so x is some x prime multiplied by 2 in power amount of letters. Okay, e and 3 multiplied by g. And y is y prime multiplied by 2 power f and by 3 power h. Yeah. Now, if you combine all this, now x prime and y prime are not divisible by 2 and 3. So we just extract all the divisors 2 and 3 from this number. So if you rewrite this equation, you get x prime multiplied by 2 power a plus e by 3 power b plus g. I actually make the life harder. So you probably get the same idea just by playing with these numbers. I just go in harder way. I just go for formulas instead of just playing with numbers. A multiply d plus h. Yep. Yeah. Okay. Now you see. So now you see. So if I want these two numbers to be equal, then x prime should be definitely equal to y prime. Yeah, because the prime factorization of this resulting number, yes, will look like this. It's prime factorization of x prime and some 2's and 3's. And here, prime factorization is y prime and some 2's and 3's. So if these two numbers are equal, then their prime factorization should be the same. Yeah. So we get this prime factorization. Take all factors 2 and 3 from this prime factorization. Yeah. And we're only left with this like core of this number. Yeah. Not divisible by 2 and 3. And this core must be the same. Okay. So it is necessary. So if I want these numbers to be equal, I need this core of the number be the same. Is it enough? No, and you easily see that it is enough. So you need to pick numbers A, B, C, and D. Can you always pick good numbers so this is equal? No, you can. Yes. So here you need, so you given numbers E and F, and you need to find numbers A and C. Can you make them such that A plus E equals to C plus F? No, you always can. Yes. So you can make one of the numbers equal 0 and another equal to difference. Yeah. So finalizing what I just told you. So instead of multiplying by 2 and 3, you divide by 2 and 3. So you take the initial numbers, divide them by 2 and 3 until you get some non-divisible core of the number. Yeah. Now, if you want to make numbers equal, you cannot change this core only by multiplying by 2 and 3. So this core must be the same. Yeah. And you can easily see that if the core is the same, then it's always possible to make the numbers equal. Yeah. You just look at these powers of 2. So for example, here we have 2 power 6 and here you have 2 power 5. Yeah. You can always multiply this by 2 and have the same power. So you take the number with smaller power of 2 and multiply it by 2 required number of times. And same with 3. Yep. So it is only possible if the core of the numbers is the same. So if number after you divide it by 2 and 3 will be the same. That's it. That's the whole idea. It's okay. It's a little bit mathematical problem, but not that difficult actually. Okay. So after you play a little bit with some divisors, prime factorizations, this thing are kind of more and more obvious to you. So after you read this problem, you think, okay, this problem about factors 2 and 3. So what we do with these factors? Okay, we look at the number, look at this number, represented as something multiplied by 2 multiplied by 3. Yeah. So it's kind of natural thing what you do. And then starting from this, you think, okay, Is it enough? And it turns out in this problem it's actually enough. Yeah. So what we're doing here? So I read the number, divide it by 2 until it's divisible, until it's not divisible, divided by 3 until not divisible. Yeah. So I get out all factors 2 and 3 from prime factorization of this number. Okay. And then I check. So again, here I have x. So I check that all these cores are the same. So okay, I do it in a strange way. So I check if it's not initialized, or if it is the same, I put x equals y. Okay, it's just strange. Okay, just a strange way to check that all numbers are the same. Okay, probably it would be much easier to put them in array and then check that all numbers in array are the same. But I decided I won't do it without arrays. So I just read these numbers and check if they are the same just on a go. So that's it. So if this if doesn't work, it means I already have some x and y is not equal to x. Then I go here, say no, and return no. If it never happened, then all numbers are equal. Every time I go to this if. Yeah. That's it. That was problem C. Any questions? No? Okay, first few problems are kind of easy. We will go to hard problems. Let's go to hard problems. Oh, D is another mathematical problem, which is actually harder than previous one. It's also some mathematical about some number theory, but slightly different. It's not about number theory, it's more about counting systems. Yeah. So we have some strange counting system with non-integer base. And hard to explain. So there are many ways how can you come to the solution of this problem. For example, what you can do, you can look at this number and have a flashback that this number sum is something about Fibonacci numbers. Yeah. So this factor is basically the ratio between consecutive Fibonacci numbers. You may think about this if you know something about golden ratio and stuff like this. Or alternatively, you can look at this formula and think it looks kind of like Fibonacci numbers. Yeah. So basically what this formula tells us. So if I have, or you may look at examples, another way to do it. So what does formula tells us? So I have a number. Yeah. So So this digit is multiplied by 1, this digit is multiplied by q, this digit multiplied by q square. Yeah. And I have this equality that q square equals to q plus 1. Basically, it tells us that 1, 1, 0, 0 is the same number as 0, 1, 1. Yeah. Let's write it here. Yeah. So this is basically the core idea of the solution, just to find this equation somehow. So you may do it by looking at this number, and so that's what's happening in Fibonacci counting system. If you didn't know, doesn't matter. So you may look at this equation and just write this. So you think, with this equation, what does it tell me about the counting system? Yes. And just see that all these three numbers kind of use in a counting system like this. Okay. Or you can look at the examples. I believe we have an example. Or here I have specific example. So even if you missed these two hints, you can go here and look at this hint. So number 100 is actually equal to 11. Okay. Okay, so this is actually the only formula that we need in this problem. Now, what else do we need in this problem? The idea of this problem is actually something that we see a lot in the competitive programming. So what we will do, we will kind of So we have some numbers which are equal. Yeah. So what we will do, we will take the representation of that number and modify it to some canonical state. So for each number, so what's the problem? For some numbers, we have different representations. So for example, if you have 1, 0, 0, 0, 1, 1, it is the same as like 0, 1, 1, 1, 0, 0. Yeah. Yeah. So it's hard to compare these numbers because they are different representation of the same number. So what I will do, I will move this number to some canonical representation. Yeah. By applying this operation. Okay, so I will try to apply this operation and move all the digits as left as possible. Yeah. Why I move digit to the left, not to the right? Because I kind of want to have a high degree of this polynomial. Hard to explain. Okay. Let's explain it like this. It's possible to move digits in both ways. So okay, so you can move digits to the left or you can move digits to the right. If you move digits to the right, then what will happen? Yeah. So if you move from 1, 0, 0 to 0, 1, 1. So if you apply this operation many times, then what will happen? So if you have like 1, 1, 1, you can apply this operation. So this 1 will move here. So you have 0, 2, 2. Surprisingly. Yeah. And now I have digit 2. Yeah. So before I had only zeros and ones, now I have also twos. And if you continue doing this, if you have a lot of ones, and you try to move them left to right, then you remove this one, you have 2, 2, 1, 1, 1, 1. Then you move this 2, you have, again, you have plus 2, so you have 4 and 3, 1, 1, 1. Then you move this 4. Again, every time you double the number, yeah? You see? So the number grows exponentially. Maybe, okay, so no, it's not okay, so it's a long number, so okay. 100,000, I believe even in Python shouldn't work, no. So even if you have some fast long number arithmetics, it shouldn't work. No, I have like, no, it should be like n squared, yeah, no, no way. So again, if I move digits left to right, I get bigger and bigger digits. I started from zeros and ones, but in the end I have huge numbers. Yeah, not good. So instead, I will move digits right to left here. Yeah, if you move digits right to left, you kind of decrease the number of digits. Yeah, so you go from 2 digits to only 1 digit. So you kind of simplify the number this way. You see? So you make the number more and more simple. You may think it's like, so you decrease the sum of digits, for example. So if you look at sum of all digits, here we have 2, here we have 1. So we decrease this number. So we kind of make the number smaller in some way. Yeah. Okay. Okay, I just want to tell you how you get intuition of what I plan to do. So I planned to apply this operation from right to left like this while I can. Yeah, and see what will happen in the end. So I can apply this operation if I have 2 neighboring ones. Yeah, so in the end I will have some number without 2 neighboring ones. So I will have some number like this. Oh, something like this. Yeah. And this will be canonical representation of the number. Okay. Now, I claim that these canonical representations can be just compared as normal numbers. So we just compare numbers left to right. And that's it, like normal numbers. Why is it? No, because every next one, so again, this q is square root of 5 plus 1 divided by 2. Yes. So if you apply it once, so q square, so let's q square actually equals to this plus 1. So it equals to, oh, okay, so let's square root plus 1 plus 2. So it's something like square root of 5 plus 3 divided by 2. Yeah. On the side said greater than 2. Yeah. So it's so each next digit is more than twice bigger than the previous digit. Yeah. So basically we have the same situation like in binary numbers, even more strict. Yeah. So in binary numbers we can compare them as strings. Yeah. So if we have two binary numbers, yeah, and something like 1 0 0 1 1, yeah, so we compare them left to right. These digits are equal, these digits are equal, these digits are not equal. Yeah. So the whole number is less than this one. Yeah, because here I have 0, here I have 1. It's true because this number have impact more than all these numbers. So this one digit has impact more than all digits here. Yeah, because this impact increases twice every time you move from one position to another. Here is something similar happens. So if I move from this digit to this digit, the weight of this digit increases more than twice. Yeah. So this digit have weight more than all previous digits in sum, in total. Yeah. That's it. So okay, during the contest, I didn't think about all of this actually. So what happened? So I'm just trying to tell you why what I'm doing actually is true. But during the contest, I didn't think about it. So because I solved like a lot of problems similar to this, I just see this picture and I think, okay, it should be something like this. Yeah. So I need to make some canonical representation. So I think, okay, this operation looks like it's simplifying the number. So I will just apply this operation, yeah, until I have some canonical representation. And probably I can just compare these canonical representations and I'll be fine. No, because it's usually how it works with counting systems. Yeah. So after you solve some problems, you just get some intuition of which tricks should work and which tricks shouldn't work. So I just felt like this trick should work in this situation, and later I may come up to some proof if I need. Yeah, but in the real contest I will not prove it. I will just feel that it should work, implement it, submit it, get accepted, and then after the contest think, okay, why it should work. Yeah, okay. Just tell you how do you actually act during the contest. Missed explanation of D. Over once again. Okay, let's do it once again. Don't have that many students today. I'll explain it once again. Explanation of D. So what we see. So we look at this equality, and this equality basically means that these two numbers represent this. So these two strings represent the same number. Yeah. No, because again, this digit multiplied by 1, this digit multiplied by q, this multiplied by q square. Yeah. So q square is the same as q plus 1. So this is q square. Yeah. This is q plus 1. Yeah. So what I will do, I will transform my number to get to some canonical representation. And the way I do it is by applying an operation which kind of simplifies the number. Yeah. And this operation is like this. So I get from 1 1 to 1 0 0. Yeah. Now I will just apply this operation multiple times. So let's see how you do it. Let's take some number. Let's 1 0 1 1 1 0 1 1 0 0 0 1 1. Yeah. So I just go from left to right. and apply this operation. So here I have 1, 1. Let's apply. Boom, boom, boom. 0, 0, 1. Oh, again, I have 1, 1. Let's apply 0, 0, 1. Yeah. Okay, it looks good, looks good. Here I have again 1, 1. Let's apply the operation 0, 0, 1. And here I have 1, 1. Let's apply 0, 0, and 1. And here I have again 1, 1. Let's put 0, 0, 1. Yep. Okay, because I always apply it to the leftmost part. So I find the leftmost time when I find the 1, 1. Yeah. Okay, so because I apply to the leftmost substring 1, 1, yeah, this number is always 0. Yeah, so I can always apply this operation. I will never get digit 2. That's important. Yeah, so I have 1, 0, 0. So you never have digit 2 when you apply these operations. Okay. That's basically it. So again, so sometimes you have chain of operations. So sometimes you have something like this. So you have, let's say, 1, 0, 1, 0, 1, 0, something like this. Yeah. So here, if I apply my operation, I remove this 1, 1, get 1, 0, 0. Again, I have 1, 1. So you remove them. And again, you have 1, 1. So you have some chain of these operations. Yeah. But again, total number of operations is not greater than 100,000. Because every time I decrease total number of ones. So I take 2 ones and get only 1. 1, 1. I don't know, how do you tell it? Single one. Okay, so it's okay. So I have 2-digit 1 and get 1-digit 1. Okay. Okay. Code is really simple actually. The whole code looks like this. I read one number, read another number, and compare them. Yeah. So this read will read this number, put it in the array of digits, and simplify it. Yeah. So here is it. I do it simple way. I make array of constant size. I always make array of maximal possible size and plus 5 just to be sure. Yeah. So I make a big array, read my string, put it into array. Then simplify it. Yeah. So I go left to right. And while I have 1 and 1 in position j and j plus 1, I remove them, put 1 in position j minus 1, and continue to position j minus 2. You see? So if I have, since I have another 1 here, yeah, maybe I again have some cascade of this operation. Yeah. So I go to position j plus minus 1 and try to continue. Yeah. That's it. So I make this series of operations. Yeah. And then move 1 to the next position. So I kind of go left to right, but when I apply the operation, I sequentially apply the operation left, 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 left until it's done, and then continue moving to the right. Okay, okay. Hope it's clear. Again, what's this? Okay, what this while is doing? This while is doing exactly this. So whenever I have situation like this, like 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, yeah, I need to apply sequence of operations. So in the end, I have so I have 1, 0, 0. Then I remove this 1 and 1. I have 0, 0, 0, 1. Again, I have 1, 1. I get 0, 0, 1. Again, I have 1, 1. I get 0, 0, 1. Yeah. So I move from here to here. I believe you can do it easily actually, but that's how I do it. So I just apply operations one by one. Every operation decrease number of digits 1. So you can just do it. Yeah. No special data structures needed here. Nothing. Yeah. Okay. Okay, that's problem D. Any more questions? No? Okay. let's move to problem E. Problem E was about chips. Problem E actually surprisingly easy. So I thought it would be much harder actually when I first read it and try to understand what's going on, but it turns out to be very easy. So what's happening in problem E? So we have some checkered field. Okay, so we have some board basically. We have board of size n by n. Yeah. Some cells are bent. We want to put some chips. So we put some chips, and the chips moves. Not here. We put it here. Yeah. So we put some chip, and the chips move to another side of the board. And we want to move all the chips simultaneously, so they never go to these bent cells. So yes. And we don't want these chips to collide. So we cannot move another chip here. So it moves here. So if this distance is the same, then these two chips may collide here. It's not allowed. No, first, let's see. So these bent cells, they basically what we do, they forbid us to use some rows or columns. So if I bend this cell, then I'm not allowed to use this row, and I'm not allowed to use this column. Yeah. So I'm not allowed to put chips in these positions. Okay. Okay, just see this. So these positions are not allowed. Okay. That's a good start, yeah? So some rows and columns just are bent. So we don't put chips in these columns, we don't put chips in these rows. Okay, now let's... That's the first part, yeah? So about the bent cells. Second part, about colliding chips. So I'm not allowed to put chips if they're colliding. So if I have one chip here, with the same distance. So these two chips are not allowed to exist at the same time. Yeah. So I'm only allowed to get one of these chips. Yeah, because they go here and then here collide. Yeah. Let's do like this. Let's just draw all the dependencies between these chips. So these two chips cannot coexist. Yeah. And these two chips cannot coexist. And these two chips cannot coexist. And these chips cannot coexist. And if you draw this, you get this nice picture of the Basically, we build a graph. Yeah. So for every edge, at least one of its ends may exist. Yeah. And this graph basically consists of cycles of size 8. Yeah. Again, you just look at the structure of what you need to find. You just look at these constraints and see, okay, what they actually tells you about the object you need to construct. Yeah, it's basically a research part of the problem. Yeah, so you look at the model given to you in the problem statement and try to play with it and see what it actually means. Yeah, because sometimes they tell you something in very difficult form, tell you very simple thing. Yeah, like here, for example. Yeah, so this looks very scary, right? But after you play a little bit with this model, you see that the model is actually not that scary. Yeah. So what's happening? I need to place chips in some positions, and I'm not allowed to put chips if they're connected to the edge. But you look, okay, so here I have cycle of size 8. Yeah. So I definitely cannot put more than 4 chips. Yeah. No, can I put 4 chips? No, I can, for example, here, 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 and here. Yeah. And now you see, so if I pick these 4 chips, they actually cover both these columns and both these rows. So if these rows and columns are not bent, you can actually cover all of them with chips. Yeah. So actually, okay, so if nothing is bent, so if no row, no column is bent, you can just play a lot of chips here, a lot of chips here, a lot of chips here, and a lot of chips here. And they will not collide, and they will cover all the rows and all the columns. Yeah. So basically the answer is the number of not bent columns and not bent rows. And then you, okay, final thing you need to see is this picture is okay in all situations except one. So the only tricky situation is when it's in the center. So for this center element, it's a little bit different. So here you don't have cycle of size 8. Here you have this click of size 4. Yeah. So out of these 4 chips, only one can exist. Good. So if you have both this row and this column, only one of them can exist. That's it. That's the whole adjustment. So we can place chips in all non-bent rows, in all non-bent columns, except one in the middle. So if both middle column and middle row are not bent, we can place only one chips, not 2. Yeah. So here we have some fixed by -1 basically. Yeah? Sometimes. Yeah. So again, answer is just number of rows and number of columns which are not bent by these bent cells, -1 if I have this situation. Okay. So you analyze general case, then analyze corner case, find this small correction, and that's it. Yeah. Code is really easy, so that's the whole code. So I read all the bent cells. For each bent cell, I bend the column, bend the row. Yeah. So this is the okay. Okay. Not very good naming, but it's computational code, doesn't matter. Yes. So in these 2 arrays, I will bend all the I will mark all bent columns and bent rows. Yeah. So I read the coordinate of the cell, bend the corresponding row, bend the corresponding column. Here I just calculate number of columns and rows which are not bent, except the board ones. So okay, so we cannot put the chip in the corner. Yeah, so we go from 1 to n-1. And in the end, I make this correction. So if n is odd, I check if both middle column and middle row are non-bent, then I make correction by 1 here. Okay, hope it was clear. So let's read some of you who didn't solve actually. Let's try to find your mistakes. Oh, it's very short. Okay, vector effect, control, complex, n. Okay. So so it will be set of bent rows. N minus 1 minus 1. No, it's not correct. Okay. So you kind of get the right idea, maybe, but this formula is definitely incorrect. Okay, the answer is kind of 2n. So how do you get this one? So you look at the empty border. So if everything is allowed, so if you have no banned cells, so what would be the answer? The answer should be kind of 2n in this situation. Yeah? So you can put a chip for every row and every column. Okay, I'm not sure what was your idea about this formula, but this part is incorrect, unfortunately. Someone else? Top sort. Okay. Okay, that's something really hard. Okay, that was something I planned to do when I first... So when I first read this problem, I think it should be something like this. Luckily, it was not. Okay, so you're actually trying to put these chips and see how they correspond to each other. Okay, I don't want to find mistakes. So it probably can be can be done like this. So probably you just have some mistakes in this code, but it would take too much time to find these mistakes. Okay, let's go to problem F. Misunderstood the problem. Oh, okay, it happens a lot, unfortunately. And it actually may be very stressful during the contest. So when you spend a lot of time, I actually had the same mistake problem G. So if you okay, I don't have normal again. So I cannot show you how much time I spent for problem G, but it was a lot. Okay, I will tell you. So we'll go to problem G. Well, F is another easy problem. I was thinking about sparing this problem for special tree contest, but now I don't think we need special contest about trees, because like in every contest we have some problem about tree, and sometimes even not the one problem. Sometimes we have many problems about trees. So again, tree is very popular topic in competitive programming. So you better learn how to deal with trees if you plan to do it. So what we do in this problem? So we have some coloring problem on the tree. So we have a tree colored with white and black colors, and we want to make all the vertices have the same color. We can do it by applying a single operation. So operation paint, just take the basically the same like in any painting application. Yeah. So you paint some vertex, and it paints a whole connected region of the same color. So if we like paint here, then all this white region will be colored to black, like here. And the question is, what is the minimal number of operations we need to make all vertices of the same color? Hard to explain how to think about this problem. Let's do it like this. What you can do, so if it's not very obvious from you from first try, start from simple things. So when you have some problem about tree, for example, you can think about problem not in a tree, but in a chain. So chain is some simple version of the tree. Yeah? So if you have not a tree, but a simple chain of elements. Yeah. So some of them are black. Let's say this black, white. Let's say black, white. Yep. Yep. So let's start with this problem first. So if we can solve this problem, we definitely can solve problem for the tree. Yeah. So this problem is definitely easier. So let's start with this problem first. Yeah. So how do you solve problem for the chain? No, if you think about it, it's quite trivial. Yeah. So what you can do is basically you have sequence of, okay, so I have here I have 1, here I have 0, I have 1, I have 0, I have 1. And what you do in a single operation, you take one of the numbers and replace it with 0. Yeah. After this three regions combined into single region 0. So basically, in every operation, you take three consecutive segments and replace them with one segment. Yeah. So you decrease number of segments by 2. Okay. No, now it's clear. So you initially have like k segments. Yeah. Then you apply the operation some number of times. You have k minus 2x segments. Yeah. So every operation removes 2 segments. Yeah. And you need this number to be at most 1. Yeah. So from here you can easily see that 2x must be greater or equal than k minus 1 divided by 2. Yeah. And that's basically the answer. So x, to x, just x. I put 2 here. So x just equals k over 2. See all this. Okay, that's one way to think about it. Another way to think about it, just to, so if you don't like formulas, like I do, I actually don't write formula usually. I just look at the examples. So I look at number of segments. So if I have one segment, the answer is 0. If I have 2 segments, 1 and 0, 0. Yeah, I need one operation. Yeah, if I have 3 segments, 1, 0, 1. I put operation here, so I need one operation. Yeah. For 4 segments, I need 2 operations. For 5 segments, I need 2 operations, and so on. Yeah. So that's what I usually write in my sketchbook, and from this, I get the formula. Okay. So I get formula not from my analytical some modifications of this thing, but just by writing some simple examples and try to guess the formula. Much easier, I really recommend. So it's much easier to get formulas like this. So you just write small examples and then guess the formula, because formula should look like something like number of segments divided by 2 plus minus 1. Yeah. So just to think this plus minus 1, it's much easier to get small examples and just guess this plus minus 1 and then go ahead. Okay. Now we solve problem for the chain. Yeah. So what happens for the tree? Let's see. What's happened here? How I solve the problem. So I take this chain, take kind of middle element, this middle element, and apply the operation to this middle element. Yeah. Can I do the same for the tree? No, yes, you kind of can. You kind of take the tree. Yeah. I'm just thinking, so I'm not, so it's just intuition, so it's not algorithm right now. So I think, okay, maybe I take some center of the tree in some sense, yeah, and just apply operation here. So I have some component here. So every time this component extends until it covers the whole tree, yeah. So basically do the same for the chain, but for the tree. You start with some center node and apply this operation until you're done. What this center node should look like? No, okay. By this picture, you can clearly see that it is kind of middle in some sense. Let's think what sense. I'm just trying to find the good some good intuition you can use in the contest, but it's actually harder than I thought. Yeah, so we kind of find so what is center of the normal tree? Center is a tree, center of the tree. Let's just drop it. Yeah, so again, it actually helps when you solve a lot of different problems from different areas, so you can combine these ideas together. So what is, for example, what we know about a tree? For a tree, it's very convenient to think about a center of the tree as the node which has minimal distance to all the leaves. Yeah, it is the same actually in a tree that just pick the center of diameter. So okay, maybe we need lecture about trees. I'm just collecting all the topics we can discuss just about the trees. So in a tree, how do we find the center of the tree? We actually do it like this. We find the diameter of the tree. In here I have, here, this is diameter of the tree, yeah? So you take the diameter of the tree and find the middle of this diameter. 1, 2, 3, 4, 5, 6, 7. Okay, let's do the, no, and so have two centers, this or this, doesn't matter which one you like most. Okay, let's take this. So the center of the diameter has very nice property. It minimizes the maximal distance to all the leaves. Okay, hope it was okay. So if you didn't know it before, we definitely need lecture. Again, it's just something we have in a lot of problems about trees. Yeah. So just tree structure looks like this. In every tree we have a diameter. It is just the longest path in a tree. Yeah. So this xy is longest path. It's called diameter. Yeah. If you look at the center of the diameter, in this point, it is the center of the tree. Main property of the center is it minimizes the distance, the maximal distance to the leaf. Yeah. So it's kind of the point which minimizes the distance to all other leaves. To all leaves, not only. Okay. So here we need to do something similar. You see? So here we need to find the point which minimizes number of operations to every tree. So again, so let's now let's go to our problem. So imagine you need to find the center. I will apply the operations to only this center. Yeah. So let's look at some leaf. So imagine here I have some leaf. So how many operations I need to apply until I cover this leaf? No, number of operations actually equals number of times I change color on this path. Yeah, so if I have like white, then I have black, and then white. Yeah. So on this path, I need to change color twice. So I need to change color here and here. See? So kind of distance from this center to this leaf equals to 2. Yeah. Again, in terms of this problem, it means I need to apply operation twice here. Well, actually 3 times. No, twice. I need to apply this operation twice to this center to cover this leaf. You see? In terms of graph, it just means I change the color 2 times. So number of times I need to apply operation actually equals to number of times I need to change the color. It is actually the same as if we make these edges of weight 1 and all edges of the same color have weight 0. It's really hard to tell you how you can get all these ideas fast. After some times, you just see them. I don't know. Okay. When I try to explain it, I actually see there are a lot of ideas that I kind of just tell you from somewhere. Yeah, it's not how it's done. So you just see that this problem looks similar to this problem, and this problem can be solved something like this. So maybe some similar approach will happen here. Okay, hope it's a little bit more clear now. So again, the full solution looks like this. I will find the center of the diameter and will apply operations to the center of diameter. Number of operations I need to apply equals to the distance to the leaf. Distance to the leaf is measured like this. If I have two edges or if I have edge between vertices of different color, then the weight is 1. If I have edge between vertices of the same color, the weight is 0. Really hard to explain. Have any questions? No? Okay, let's read the code. Code is really simple. Okay, so the idea is kind of complicated if you never did it before. If you done it before a couple of times, you kind of see this pattern, so you see what you need to do. Yeah, and then you think why you need to do this. Again, code itself is really simple. I just find the diameter of the graph with these weights. Yeah. So how I find diameter? Like many ways to find the diameter. I usually do it like this. I start from node 0, find the farthest node. Then start this farthest node, find the second farthest node. So I just run DFS twice. Yeah. So the way I find the diameter usually is like this. It's just easier to code, easier to understand. So you start from node 1, from node 0 again. Let's count from 0. Find the farthest possible node x. Then from node x, you find the farthest possible node y. Yeah. And now this xy is a diameter. It's very easy. So let's see. So this I find node x, then find the diameter. So this DFS actually finds the diameter and the farthest node. Yeah. So simple DFS, like normal for trees, x, my parent, and the current distance. Yeah. And here I call DFS of y, distance plus weight of the edge. Yeah, so it's 0 if they're equal, 1 if they're not equal. Yeah, see? And just calculate maximum of all of this. That's it. That's very, very simple code. So this DFS find the maximal distance from the starting node. Yeah, and I call it twice. I take any node like 0, find the farthest node from 0, x, then take this x, find the farthest node from it, and I have a diameter. Then the result is just half of the diameter. Okay, I don't know what to tell else about this problem. Equally distance from the edges. What? From the edges. From the leaves, yes, no, yes. I want to find like the middle node, which is have equal distance to the leaves. Yes. So I just start from this middle point and like go in both directions and like minimize distance to all the leaves. Yeah. It kind of makes sense. So if you would wanna do it in minimal number of first, so after you believe it's always doable, if you start just from a single point and just apply operations to only this point, everything else is kind of trivial. Okay, that's it. That's problem F. Did anyone solve problem F? Problem F is actually solvable. So G is hard, no, harder than usually. H is very hard. Okay. F is solvable. I believe you can do it. So if you didn't solve problem F during the contest, solve it later. Oh, Alex solved it. Good. Just try to do it. It's not very, like you see, code is very simple. Okay. Or use BFS. Why you need BFS? Okay, not sure why you need BFS. Priority queue for tree. Really? Okay, you don't need BFS. It's tree. Just you can do it using BFS. Okay, but for the tree, you don't need BFS. It still works. I agree. Okay. Whew, we have two problems left. Let's go. Problem G, I misread it for the first try. When I first time read this problem, I misread it. So I was thinking that okay, so its total amount of people should go into town before this truck. I thought so before my truck, I should have at least L people. So if I have more than L people, it's still okay because it kind of fits to the story. So if I have more people, the driver should be less afraid, just based on the story. But okay, it's not how competitive programming works. So you read the story, but you need kind of read it formally. So if you can deduce some facts not told you specifically in the story. Yeah. Okay, that's fine. So if you need at least L before and at least R after, it's also a very fun problem actually. I spent a lot of time just solving this problem, and then I implemented this code, and then I look at the first example and thought, wait, why we can take all of them? So we can take all 5. So for both these people, there are at least 3 before and at least 0 after. Why we dropped the 4th track? We can take all 5 of them. And then I go back, read the problem once again, think, okay, so total number of people, so exactly this. And need to solve another problem. And a completely different problem. So it happens. Don't be harsh to yourself. So if sometimes you solve different problems, spend extra hour, welcome to the club. It happens. Okay, so it's okay. So how to solve this problem? This problem is actually a little bit easier than the problem I solved first. First of all, what we have? So we have some buses. For every bus, we know the number of people in this bus, like CI. Yeah, we know number of people before this bus, LI, and number of people after this bus, like RI. Yeah, and if you combine all these numbers, you get total number of people. Yeah, so all the people are either before the bus, in the bus, or after the bus. Yeah, so if we take this bus, then the total number of people we take should be equal to this sum. Yeah. From now on, we just can split. We can just split all the buses into groups with the same sum. Yeah. So let's say like Ki equals Li plus Ci. Yeah. And we just combine all the people with the same parameter into some class. And then when we have basically several independent problems, yeah, so we cannot combine buses from different classes because total number is different. Yeah, that's it. So just split problems into several independent problems. So we need to solve problem for all different values of k. That's the first step. Second step is actually similar to the one we had. Similar problem in last year youth challenge, when you had a number. For each number you calculate sum before and sum after. What's actually happening in this situation is, okay, so So if you look at some drivers or some buses which we can combine, yeah. So imagine we combine some buses. So it's like C1, C2. Yeah. For every bus, so this sum must be equal to L3. This sum must be equal to R3. Yeah. So every bus have kind of fixed position in this order. See? Yeah. You can think about it like this. So every bus is an edge, actually. So is an edge from this point to this point. And what we're looking for the path from 0 to k. K is the sum. Yeah. Okay, so every bus is edge from, so before this bus I had L people, after this bus I have L plus C people. So kind of every bus is a transition from this number of people to this number of people. Yeah. And I want to get these transitions so I have k people in total in the end. So I need to take these transitions with maximal total value. So in the end, so I start with 0 people and end with k people. That's actually pretty standard dynamic programming problem. Yeah. So what I will do for each position here. So this k is not very, so this k is up to, so k is not greater than sum of this L plus L plus C. So k is not greater than, let's say 3 like 10 power 5. Yeah. So k is pretty small. Total number of people is pretty small. So what I will do, for every position here, for every number of people from 0 to k, I will find the maximal value of buses which can move me to this position. Okay, let's write it like this. Let's say d of I will be, like this is d of x. So I will be index of the bus. Will be maximal value of buses with x people in total. Yeah. So I already put some buses. Total amount of people is x. Yeah. And I just remember this value. So every time you take a new bus, you just make one update of this array. So you go from D. So before this bus, you must have Li people. And after this bus, you have L plus C number of people. Yeah. So you make this transition. So every time you take the bus, you make transition from here to here. Update your dynamic programming. So you might make one relaxation of your dynamic programming. Yeah. And that's it. And then in the end, look what will happen in the end. You also need to construct this array, so you need backwards pointers and so on, but it's all technical stuff. So after you solve like a few thousands of dynamic programming problems, it's just technical difficulties, very small actually. So that's it. That's the whole code actually. It's pretty short. Let's look at it. Here, I split all elements into classes. Yeah. So for each element, x not equal n. No, you don't need this. Something strange. It was from some previous code. Okay. So for each bus, I calculate this sum. No? Now for each sum, I will maintain a list of buses with the same sum. See? Here, I will iterate over these classes. So K is total number of people in this class, and AA is just vector of all buses. Here I will iterate over all the buses in this class and update my dynamic programming. So here, okay, because I need backwards pointer, it's a little bit overcomplicated, yes, but it's actually easy. So I calculate this value and update it. Okay, I also need to update backwards pointer here and remember which bus is now here. So this part is just technical to restore the final answer. That's it. So intellectual part is actually this. So I make this one transition from here to here. So yeah. So I make I take value d li, add the value of the bus, then look at the value in this position, check if my value is better, then update it. Yeah. So this one relaxation in dynamic programming with some backwards pointer because we need to restore the answer. Yeah. In the end, if I have, okay, we don't need this also. Some old version, okay. So if my answer is better, I will restore the answer using this backwards pointer. Yeah. That's it. Also, I reuse the same array here. So I reuse the same array D for all the classes. And to make it faster, I actually here carefully move it back. So so initially all elements are minus infinities. I put some values in them, but I only put in these positions. So I restore only these positions. So I don't need to fill this array with minimums again. Yeah. So I carefully restore the positions I changed. I believe it can be done with just sets. Yeah, you probably can just use set here. I do it really carefully because I want a linear complexity. You can do it using simple set and just get the same thing. Yeah. It will multiply it by log, but I believe it's enough. 10 power 5, yes, it should be enough. Yeah. So that's it. So again, pretty short code. It's pretty intense, yes. So we need to think to get this code. But again, the few ideas are like this. First, you need to split all buses into classes. For each class, you know the position of this bus. So your position is this. Before this bus, you have this number of people. After the bus, you have this number of people. Yeah. So every bus is like move from this number of people to this number of people. Yeah. And if you think of buses in this way, you build the graph, make dynamic programming. All the rest is actually technical part just of dynamic programming. So after you solve, again, some more problem dynamic programming, it's not the problem anymore. So the only problem is to get all these ideas. After this, implementation of dynamic programming is not, it's pretty trivial actually. So you just implement it like you normally implement dynamic programming. Nothing really interesting here. Okay, this problem G. Any more questions? Any more questions? No? Last problem. Let's go. Problem H. Let's go. Problem H is actually a very fun problem. I'm not sure what is the difficulty of this problem on code forces. Let me check. Ah, 260. Okay, or 2,600. Okay, not the easiest problem we usually have, but okay, 200 to 2,600 should be approachable for you. It's okay. It's already kind of master level problem. Okay, maybe even close to Grandmaster level problem, but it's doable. Okay, no rocket science here. So this is the whole code. It's okay. It's longer than usual. Okay, it's actually fun. So let's see. So what we do in this problem? We need to kill some monsters. Let's see. So okay, let me draw some pictures. So we need to kill some monsters. What's the problem? Sometimes to kill the monster, we have to kill some another monster first. So we have some gun here. So this is the gun. Yeah. And we have some monster. Okay, how to wish? Let's say X is the gun, and we have some monsters. Yeah. Now to kill this monster, we need to kill these two monsters before, because they kind of on the side of the fire. Yeah. So we cannot fire from here to here without killing these monsters first. So we need. So if I want to kill these monsters using this gun, I need to neutralize these two monsters first. So I need to take two another guns to kill this monster, and another gun to kill this monster. Yeah. So now I can kill this monster. But again, to kill these monsters, maybe there's some another monster here. So if you want to kill this monster using this gun, you need to kill this monster first. So you need some another gun to kill this monster. Yeah. So situation get more and more complicated every time you add some more gun. But let's look at the constraints. If you look at constraints, you immediately see this number 7. It looks like very it stands out from this constraint. Yeah, so it's really small. Yeah. So if you have some really small number, actually you need to use it. Yeah. So we build all this picture. It cannot be a very branching. Yeah. So every time we do something, we use one gun. So we imagine we want to kill this monster. We choose this gun to kill this monster. There are only 7 possible guns to kill this monster. So after we choose this gun, we need to kill this monster. So for each of these monsters, we need to choose some gun, which is not used before. Let's choose this gun for this monster, this gun for this monster. Again, we have some monster we need to kill. We need to choose gun. We will very fast get out of guns. Yeah, because we only have 6 possible guns. Yeah. So that's the idea. We will carefully do this backtracking, trying to kill all the monsters we need to kill in order to kill this final monster. Yeah. Just make this okay, just cascading kills again. So I need to kill this monster using this gun. To do this, I need to kill these 2 monsters. Yeah. To kill these 2 monsters, for example, I use this gun. And every time you don't know which gun to use, but you only have 7 of them. Yeah. So you can check all of them. It's called recursive backtracking algorithm. Yeah. So every time we don't know which way to go, we just recursively try all of them. We have only 7 of them. Yeah. That's it. Now, okay, I actually oversimplify. Okay, I don't know why, because experience. I will show you. So my code actually works in 7.7. I didn't try to optimize it very well, actually. But even my first attempt works in less than 100 milliseconds with 3 seconds time limit. So it's just something I do intuitively. I oversimplify this code, over optimize it. You probably can write less optimized code and still fit into time limits. But okay. So the way I implemented it, I implemented like this. So to make this code work fast, yeah, I need to pre-calculate the following. So for each monster and each gun, I will pre-calculate which other monsters I need to kill before. So this is something I will calculate before I do backtracking. So for each pair of monster and gun, so I have gun number I, monster number J. Yes, I will put all these monsters into some specific array. I call it, let's do it, obstacles, okay? Obst of I and J. Yeah. So for each pair of monster and gun, I will put all the monsters I need to kill before into this array. And I can do it fast, actually. I do it fast like this. I take the gun, I take all the monsters, and again, I will classify them by the direction. So for each direction, I will take all monsters in this direction. And for each of them, add all previous in this array. That's it. Let's read the code actually carefully. This code is actually interesting, so it's a lot of it. So let's read it carefully. I didn't use any pre-written code here. I just don't use any pre-written geometry here. We don't need actually. Let's see. So I read all the coordinates. Here, what we do? I take all the guns one by one. For each guns, I take all the monsters. For each monster, I kind of want to find the direction to this monster. So I take this direction, dx, dy. So this is my direction. Yeah. Now I want to classify all the monsters in the same direction. Yeah. To do this, I will do the following. I will move this direction to some canonical form. And in integer coordinates, it's easily done by just dividing them by greatest common divisor. Yeah? So I find greatest common divisor and divide both these numbers by this divisor. Okay. Now this dx dy is basically my direction. So I will use this pair as a key in my map. Yeah, so for every direction, I will get list of all monsters in this direction. Okay. Now, I need to sort these monsters by distance. So instead of normal distance, I will use Manhattan distance because it's the same. So I need distance to only distinguish which monster is closer, which monster is far away. Yeah. So to make this comparison, I can use any metric actually, and this metric is cool because it's simple and it's integer. You can use Euclidean distance, also will work, but you will not have integers. Yeah, not very nice. You can use square of Euclidean metrics, so it's like dx square plus dy square. Also will work, but then you have large numbers. Yeah, Manhattan distance use small numbers and it's integer, so that's why I prefer use it here. But it's actually not important. You can use any metric here. Yeah, so it's just number used for sorting monsters by distance. Okay, here I take every direction, take all the monsters in this direction, sort them by distance. Yeah. Now I take these monsters one by one. Okay, another cheat I used here. If I have if I have more than k monsters before, I definitely cannot kill this monster. Yeah, because I have only k guns. I cannot kill all the monsters before. So if I have more than k monsters before it, I just put -1. So this -1 indicates I cannot kill this monster with this gun. If not, I put all previous monsters into this list. Okay, so this is pre-calculation. For every pair of gun and monster, I pre-calculate what happens if I try to kill this monster with this gun. I either cannot do it if it's -1, just impossible, or I need to kill this list of monsters before. Okay, that's it. Now I just call recursive backtracking. So this function kill is recursive function. It tells kill me please this list of monsters. So initially I give it only one monster. I tell kill this monster please. If it is possible, I increase the answer. Okay. What this function does? This function tries to kill this set of monsters. If set is empty, I'm done. It's okay. Yeah. If set is not empty, I see how many guns I have. If I don't have enough guns, I immediately turn false. Okay, here I actually over optimize. Okay, because that's how you normally do backtracking. So normally when you do backtracking, you want to do some things like this. So if you see that the answer is impossible, you just stop the backtracking here. I believe if you remove this, you will still pass all the tests. Now, if nothing of this happens, then I actually try to kill this monster. So I take the first monster from the list, from the set. Yeah, you take any monster from the set and try to kill this specific monster. Yeah, check. You choose which gun you use. If it's not used, if it's possible, so if it's -1, it's just impossible. Continue. If it's possible to kill this monster with this gun, then you do something. Then you try to kill this monster with gun. Yeah. Now you mark this gun as used. Get new set of killed monsters. So you need to kill all the same monsters except monster J, and you need to add all monsters on this way. Yeah. Okay. So you get new set of monsters you need to kill. Remove this. Add all these monsters. Now you have a new set. Okay. Try to kill this new set of monsters. If you succeed, you return true. Okay. I also clean erase after I'm doing it. So I have this erase alive and used to see which monsters are alive and which guns are used. And I change it here. I also like to clean it after. So that's how you normally implement backtracking. Yeah. So you do recursive call. So you change something, do recursive call, and then undo this to clean the erase back. Yeah. That's it. If you tried all the guns, nothing worked, then you return false. That's it. Pretty simple code if you think about it. It's not standard code. It's not like not some standard algorithm. Okay, it's not just some implementation. It's actually something strange. Yes. So it's backtracking. It's not happening that often nowadays. So, but I actually highly recommend you to solve this problem. So if you didn't solve this problem during the contest, try to solve it later. Just try to at least write your own backtracking algorithm. It's actually quite helpful in many cases. So in some problems, you just not sure what you do. So you just implement some backtracking and see what will happen. Is it readable? It's also backtracking, but you don't do it recursively. You do it by next permutation. You just take all the permutations of the guns, I suppose. Yeah. And for every permutation of the guns, you check which monsters you can kill. One of the mistakes you can make here is actually that you can forget that the same monster can be killed multiple times if you try to do it. So you need to remember which monsters are already killed. For example, let's say, so I want to kill this monster, and I have two monsters in the middle here, one and here another. Yeah. So I want to try to kill this monster with this gun. To do this, I need to kill these two monsters first, and I have two guns here. This gun tried to kill this monster. This gun tries to kill this monster. But here in the middle, I have another monster. Yeah. So I can neutralize this monster with another gun, this gun. And then I will be able to kill both these monsters and then kill this monster. Okay, now imagine I cannot kill it, so I have a lot of a lot of monsters blocking this view, a lot of monsters blocking this view, and so on. Yeah. So I cannot just kill this monster immediately. Yes, I need to do it some hard way. Yeah. So I need to remove this. Okay, and I cannot kill this, and I cannot kill this. Yeah. So I just it's easy to block the view. You just put a lot of monsters here. So, yeah. So imagine all other ways are blocked, so you only can kill these monsters. Yeah. So yeah. So you can do it like this. So this gun kills this monster in the middle, and now you can kill both this monster and this monster. And now you open the way for this gun to kill this monster. See? So this monster blocks two guns here. Yeah, but we need to kill it only once. That's probably that's one of the possible problems here. So when you do backtracking, you find this monster twice. You find it when you try to kill this monster, and you find again when you try to find this monster. But you don't need to kill it twice. You need to kill it only once. That's one possible mistake I can see in this problem. I'm not sure what's happening here. It's too complicated. Sorry. I cannot read this code there that fast without your comments. If you don't have any more questions, let's finish. Okay, so try to solve the problems, especially the last one. I believe last problem is actually not that hard, so you can do it. Okay, so that's it for today. Okay, contest 6. See you next week.